Today I want to talk about plate tectonics, and we're going to start talking about plate tectonics with a picture of the Earth. So let's go ahead and draw a picture of the Earth. So there's the surface of the Earth, and then we're going to go inside the Earth. So this is going to be a cross-section of the planet. And the planet is made up of layers. It's going to have an outer layer called the crust. Sort of a middle layer called the mantle. These last two layers here, these inner layers, are the core, which you've got an outer core and an inner core. Now, what makes these layers different from each other is their chemical composition. That's how these layers are divided up, based on their chemical composition. There's different types of rocks found in each one of these layers. The crust also has a lot of oxygen in it. Oxygen is very reactive, so oxygen reacts with a lot of the rocks here. For example, calcium carbonate, iron oxide. So oxygen is one of the most prevalent elements in the crust layer of the Earth. And then we've got the mantle, the outer core, the inner core, and the core contains a lot of iron and a lot of nickel. Very heavy elements. And we're going to talk about why that is in just a little bit. Now I also want to add in here another layer. And this next layer is going to consist of the outer part of the mantle and the crust. So I'm going to show it like this. And this is going to be called the lithosphere. The lithosphere. And the lithosphere is going to be solid, where most of the mantle right here is going to be like a thick liquid. A thick liquid. I like to think of it as like a really viscous or really thick honey. And then we've got the outer core. This is actually going to be more liquidy. And then finally the inner core, which is going to be solid. Even though the inner core is the hottest part of the Earth, there's so much pressure on this inner core here that it actually forces it to be solid. Now, let's go ahead and take another look at what's going on here. We've got a lot of heat being generated in here. And this heat is going to come from, is going to occur due to several reasons. And let's talk about where this heat actually comes from. So one reason why we've got a lot of heat here is due to when the Earth was formed. Gravity pulled all these elements, all these materials together. And all these materials were under tremendous pressure, and pressure creates heat. So there's still heat left over in the Earth from when it was formed 4.6 billion years ago. So I'm going to write down when the Earth was formed. The heat and pressure when the Earth was actually formed. Still there. Number two, there's a process called differentiation going on. So differentiation. Now, differentiation means that we're going to have different layers of rock. And the reason is when the Earth was formed, all the elements and all the rocks were pretty much uniformly spread out here. But over time, gravity pulled the heaviest or densest materials towards the center. So over time, iron and nickel sort of sank because they were heavier and more dense materials. And the lighter materials sort of stayed near the surface. So there was a sifting process going on here. Now you can think of this as these iron and nickel and other heavy materials actually sank. They got dragged through this very thick, liquidy layer. And that created a lot of friction, and friction creates heat. So we've still got a lot of heat left over from that differentiation process, which is still occurring today. And the third reason, and this is probably the biggest reason of all, is radioactive decay. Radioactive decay. Radioactive decay of uranium, thorium, and potassium. So you've got a lot of radioactive decay, and as we know from nuclear reactors, radioactive decay creates a lot of heat. And probably the vast majority of heat, maybe 90% or more, who knows, is due to this radioactive decay. And this generates, still today, tremendous amounts of heat inside the Earth. And we all know that heat rises. Simple physics. Things that are really hot expand, they become less dense, and they rise up. And that is going on. When we say rise up, we're talking about moves away from the center here, because up is relative, right? So what's actually going on here? Well, we've got heat rising. And most of this rising occurs in the really thick liquid mantle here. So what's going on is this. You've got massive convection currents going on. You've got thick liquid rising due to its extreme heat. It expands and it rises. And this is rising up, rising up, rising up, rising up. It rises up to about the lithosphere where it actually becomes solid. And then obviously that thick liquid can't rise through that solid layer. So it rises up to that point and it actually begins to spread out. Spread out. Now, as that thick magma, as it rises up, it begins to cool, cools. And as things cool, the molecules actually become closer together. And the closer together those molecules become, the more dense that material becomes, and it begins to sink again. So as it cools, this magma begins to sink, And this is going on everywhere. It's going on here too. It's rising and sinking. Rising and sinking. And it goes on everywhere here. And these are called convective cells or convection cells. And this has a huge significance because the solid portion of the Earth, the lithosphere, is actually broken up into, we can think of it as puzzle pieces. It's broken up into many puzzle pieces. And these pieces actually move around relative to each other about, on average, about an inch a year. They're moving away from each other. Some of them are moving together. Some of them are moving against each other. About, on average, an inch a year, give or take a little bit. And we can actually check this with global positioning satellites to almost the millimeter. So we know what's going on here. Now, think about what's happening here. As this magma rises and cools and spreads, the solid lithospheric plate, that's what a tectonic plate is. We're talking puzzle pieces of lithosphere. So you can think of them as lithospheric plates, but the proper name is tectonic plates. These tectonic plates are actually, in this region, they're moving away from each other. And we've got a special name for that. That is referred to as a divergent boundary. So I'm going to go ahead and write that down up here. A divergent boundary. And what's happening here is the plates are actually moving away from each other. So we're creating new landmass there. As this magma comes up, we're actually creating new landmass, new material, new land right there. And a good example of this is seafloor spreading, the mid-Atlantic ridge. Right down the middle of the Atlantic Ocean, you've got a huge crack in which the seafloor is broken open. We have hot magma coming up, creating new land. In fact, the biggest mountains in the world are underwater right here in the Atlantic Ocean. So we could say, we could call it the Mid-Atlantic Ridge. And that actually creates new land. Now look over here. Over here, we've got a tectonic plate moving this direction, and over here, we've got a tectonic plate moving in that direction. And these plates are actually being dragged along with the convection current. So these convection currents, due to friction, as these huge plumes of magma move, they actually drag these overlying puzzle pieces or tectonic plates with them. So these two tectonic plates are being dragged towards each other here. And that is referred to as a convergent boundary. So I'm going to go ahead and I'm going to write that down over here. Convergent boundary. Now with a convergent boundary, we've got two tectonic plates coming together. They're crashing into each other. One's going that way, one's going that way. But we actually have two subgroups of convergent boundaries. We've got one between continental tectonic plates. So if you've got a, let's call it a continental and continental tectonic plate, if we got two continental tectonic plates crashing into each other, they're about the same weight, they're about the same density, and what's going to happen is they're going to come together, they can't go down, so boom, they move up like that, and they create mountains. So that's what's actually going on there. You've got this sort of thing. They're crashing into each other, and they're creating mountains. Mountains. And a good example of this is the Himalaya Mountains. And also the Appalachian Mountains. Now, another example of a convergent boundary is between an oceanic plate, an oceanic tectonic plate, and a continental plate. So we've got I'll put continental plate and an oceanic plate. Now, the oceanic plate is going to be denser. Think about that. You've got all this water crunching down, pressing down on the rock below. That's going to make it very dense, very heavy. Also, oceanic plates, for several reasons, contain a lot of iron. And iron itself is going to be very dense. It's a very heavy material. So the oceanic plate tends to be the denser of the two, the denser or heavier of the two. So what's going to happen here is your continental plate is going to go one way, your oceanic plate is going to bump into it, but it's actually going to dive below because it's heavier, it's denser, so it's going to sink, it's going to dive below. And this is actually, it's going to dive below. Another name for dive is subduct. So this is an example of subduction. And what's going to happen here is this. As the oceanic plate dives or subducts here, this material is going to become very hot just due to the pressure. You're pushing all that rock, you're squashing it on down there, plus you've got the heat of the earth down there. So all this new rock, all this rock is coming down here under a lot of heat and pressure. It's going to begin to melt. And as things melt, they begin to heat up, they begin to expand, and it begins to rise up. And what we're actually going to produce there is volcanic mountains. So where you got a lot of subduction taking place, you end up with volcanic mountains. Volcanic mountains. Let me fix that there. Volcanic mountains. And a good example of volcanic mountains is the Andes Mountains in South America. One of the longest mountain ranges in the world. And they have a lot of active volcanoes down there. And these are some big mountains too. Some of these peaks are over 20,000 feet high. An excellent example of subduction. Now also take a look right here, where the oceanic plate dives right here below. You're going to get a big indentation there. You're going to, where this actually dives down, it's going to drag the Earth down right there, and you can get a pretty deep hole right there. And a good example of that is the Marianas Trench, one of the deepest places. I think it's over 30,000 feet deep on planet Earth. Really, really, really deep hole there due to one plate subducting beneath another plate. Now, the third type of boundary we can have, and you can't see it that well on the actual diagram, but if you have two tectonic plates, and they can actually be moving past each other, they're moving parallel to each other, but in opposite directions. This is going to be called a transform boundary. A transform boundary. And what's going to happen here is you're going to have two tectonic plates. They're going to be moving past each other, and as they do, they tend to stick, and then they break loose, and then they stick, and then they break loose. And every time they break loose and start to move, that actually creates a lot of vibration. And those vibrations are referred to as earthquakes. So these transform boundaries oftentimes are responsible for earthquakes. A good example, or probably one of the best examples of a transform boundary, is the San Andreas Fault out in California. So let's go ahead and write that down. San Andreas Fault. And a fault is just a crack. That's all it is. A fault line is a crack. So you've got the crack in the earth, and you've got one tectonic plate moving one way, one tectonic plate moving the opposite way as they pass each other. Now, let's go ahead and we'll try to draw California here as best I can. So there's California. And you've got San Francisco. San Francisco right there. SF, San Francisco. And down here you've got LA, Los Angeles. And this fault line actually goes right between the two. And LA, as it turns out, is moving north. And San Francisco is actually moving south. And that's why we have a lot of earthquakes out in California, because you've got a major fault line right there. Now, what type of ramifications does this have? Well, you can see that these two cities are moving in opposite directions. And we actually know how fast these plates are moving relative to each other. So if everything goes as it currently is, and there's no reason to believe it won't, these two cities are literally going to pass each other in about 20 million years. Yep, they're going to pass each other in about 20 million years. So something interesting to think about there. Now I want to follow up on that just a little bit more, and I want to talk about earthquakes. Earthquakes are going to produce vibrations. And these vibrations are waves. That's what a wave is. It's a vibration for the most part. And earthquakes are going to produce two types of waves. And I'm going to go ahead and I'm going to erase my diagram of California here. But the two types of waves are going to be referred to as P waves. P for primary. And P waves, at least in physics, are referred to as longitudinal waves. They're longitudinal waves. Now, what that means is the particles vibrate back and forth. So if my fist is a particle or a piece of rock, and my other fist is another piece of rock, what happens with the P wave is this rock moves this way, bumps into this particle or this rock, and then snaps back. And then this rock, just like a billiard ball, moves in the same direction and bumps into another particle or rock, and then it snaps back. And it's sort of like a domino effect. One particle bumps into the next particle, which then bumps into the next particle, which then bumps into the next particle and snaps back. And you've got this domino effect. That's a longitudinal wave. These longitudinal waves tend to be very fast. So I'm going to spell it with a P, fast. So we can remember P for primary wave, P for fast. They tend to be fast moving, and they tend to pass through solids and liquids both. Solids and liquids both. The next wave that's produced, and they're both, by the way, both of these waves are produced at the same time, is going to be an S wave for secondary wave. And secondary waves are transverse waves, which means that the particles vibrate up and down. So if my hands are particles, one particle vibrates up and then down, and then the next particle vibrates up and then down, and as the wave moves through it, that wave of energy, the next particle up and down, up and down. So that's what a transverse wave is. Remember, it's a wave of energy, and as that wave of energy interacts with the particle in response to that wave of energy moves up, down, and then the next one up, down, next one up, down. So that's what's actually going on here. These secondary waves tend to be slower, and that's why they're called secondary waves, because they reach a point on the Earth a little bit later than the primary wave. So they're called secondary waves. They're the second to arrive. So they tend to be slower, and they actually pass through only solids. They pass through only solids. And it's these waves, these secondary waves, I'll do it in red, these secondary waves here, they do most of the damage on the Earth. These secondary waves, with a little contribution from the primary waves, but it's most of the secondary waves. When an earthquake happens, it's the secondary waves that create most of the destruction and damage on the surface. And let's go ahead and take a look at that. So again, I'm going to draw a picture of the Earth here. There's the Earth. And let's say an earthquake occurs here, inside the Earth. And that's where it usually happens, inside the Earth. That's called the focus. And that's where the earthquake happens. The focus. And then the point directly above that, on the Earth, is going to be called the epicenter. And the epicenter is directly above it. And this is where the earthquake, EQ, earthquake, is felt. Directly above it, oftentimes. And outward from this focus are shock waves, are waves, both P waves and transverse waves. Now earthquakes, I want to go into just a little bit more. You can measure earthquakes on the Richter scale. We've all heard of that, the Richter scale. But what does that actually mean, the Richter scale? So if I actually draw a scale here, I'm just going to put in some numbers here. 2, 3, 4, 5, 6, 7. So what do these numbers actually mean? Well, it turns out that 4 is about 10 times stronger than 3. And 5 is about 10 times stronger than 4. And 6 is about 10 times stronger than 5. So you might say, well, how much stronger is a 6 compared to a 3? Well, this is actually kind of logarithmic. So what we're going to do here is we're going to take the 10, the 10, and the 10, and we're going to multiply them together, and we get 1,000. So an earthquake that has a magnitude of 6 is 1,000 times stronger than an earthquake that has a magnitude of 3, because it's logarithmic. That's how this scale is created. It's logarithmic in nature. Now, I want to go back to tectonic plates for just a minute and sort of finish up there. I want to talk about Alfred Wegener, the person that actually thought up this idea of tectonic plates. So let's go ahead. I'm going to erase some of this over here, and I'm going to talk about Alfred Wegener. So I'm going to write his name down up here. Alfred Wegener. And he thought up this idea of continental drift. This idea that continents actually move around on the surface of the Earth. He didn't know how far at the time. We now know approximately an inch, but he knew that they moved around, and he theorized back millions and millions and millions of years ago that all the continents were actually together into a supercontinent called Pangaea. And then over time, as these continents, these plates, as these continents moved apart from each other, they actually moved to different locations on the surface of the Earth. And there's actually evidence to suggest this. Antarctica, actually, if you dig down under all that snow and ice, contains the remnants of an ancient pine forest. So obviously, pine trees are not going to grow on the South Pole where it's that cold. So Antarctica must have been much closer to the equator a long time ago. Anyhow, Alfred Wegener back in the early 1920s created this idea of continental drift. And again, the tectonic plates or continents drifted apart from each other. And he based this on several bits of scientific information. One, continent shape. If we actually look at a map of the continents, and we can imagine all these continents kind of put together, it looks like they kind of fit together relatively well. People laughed at that back then. Today they're not laughing anymore because it sounds like it actually works out to be very true. So that's one of the bits of scientific information. Another bit of scientific information was the idea of rock formations. Rock formations. If we actually look at the rock formations on the coast of one continent and the rock formations on the coast of another continent, they actually look pretty similar to each other. They mesh up pretty well. And then finally, fossils. If we dig up and we find some fossils on the coast of one continent and we dig up some fossils on the coast of another continent, they're actually very, very similar. What does this mean? Well, it means, at least according to Alfred Wegener, that these two continents were once together. They were one. And these animals roamed around sort of free in that whole area. And then over time, after these fossils were formed, these continents moved apart. And that seems to fit pretty well with this Alfred Wegener's idea of continental drift. Now, later on, we actually found more information to support this. And some of the other bits of information we found was that if we look where the seafloor is spreading, right here, where we have a divergent boundary, mid-Atlantic ridge, if we look at the mid-Atlantic ridge, notice new rock is actually being formed right here. That's where new rock is being formed. That is new, young rock. And then as this rock hardens and solidifies and moves away, as this rock moves away in both directions, that rock is going to become older and older and older. So here's the youngest rock, and as we move further away, the rock should be older and older and older and older. And if we radioactively date that rock, that is exactly what we find. We find that the rock gets progressively older as you move away from where the seafloor is actually spreading. So let me write that down. Progressively older rock further from seafloor spreading. And then a final bit of information, and there's actually more on top of this, but this is another good point, that if we take a look at the rock as it moves it further and further and further away, this is occurring over hundreds of thousands to millions of years. And we know nowadays that about every 100,000 years, the magnetic field of the Earth actually changes direction. So what you end up with is bands of rock, alternating bands of rock. So I guess I'll do this in different colors. There's one band of rock. There's another band of rock. Then another band of rock, and these bands are approximately 100,000 years old. Another band of rock. And if we look at the magnetic materials that the rocks are actually made up of, we can see that the materials, the atoms, are actually pointed in opposite directions, lining up with the magnetic field of the Earth at that point in time. So you've got these alternating magnetic bands that are approximately 100,000 years old, corresponding with, you know, that the Earth is changing its magnetic field every 100,000 years. So let's go ahead and write that down. Alternating magnetic rock bands. And that's all the information I'm going to include here. Now, taking this information and combine it with this information, and we're going to call this newer or more modern theory, we're going to call this the theory of plate tectonics. The theory of plate tectonics. And remember, a theory, a scientific theory, is a little bit different than a theory that we use in the general public speech. A scientific theory is a well-established explanation for why something happens based on lots and lots and lots of information. And that's exactly what this theory of plate tectonics is. It's a scientific explanation consisting of lots and lots of information as to why something is happening. In this case, why the continents are actually moving around. The tectonic plates are moving around relative to each other. And that's it for tectonic plates.